All right. So welcome to the second talk of the day. We have Thomas Korber talking about the Penrose inequality in extrinsic geometry. Whenever you're ready, you may start.
Yeah, thanks a lot for the introduction and also for inviting me to give a talk here today, which is very nice. So I hope you can enjoy my talk despite the technical issues. But yeah, so as has been said, I'll talk about a recent joint work with Michael Eichmair where we work on a conjecture of Gerhard Huisken on a Penrose inequality in extrinsic geometry, which is, of course, related to the Riemannian Penrose inequality. And to put this result a little bit into perspective, I want to start with a bit of background on the Riemannian Penrose inequality. And to this end, we're going to consider a connected complete Riemannian three-manifold, which I'm going to call MG. And let's assume there's integrable scalar curvature. Okay, and we're going to assume that MG is asymptotically flat, so I'm not going to define what this means, but basically this just means that outside of a large compact set, the manifold MG looks very much like Euclidean space. So within some bounded region, the geometry and topology of MG might be very complicated, but once you leave this compact set, MG starts looking more and more flat. Okay, so in mathematical relativity, people are very interested in these asymptotically flat Riemannian three-manifolds, and the reason is that they model initial data for the Einstein field equations for isolated gravitational systems. So the picture you should have in mind is of a large space-time, with a few number of large masses, such as stars and black holes. And now if an observer moves far away from these masses, he or she is going to feel a little gravity corresponding to the space-time and also initial data for the space-time being asymptotically flat. Okay, now in this physical setting, there's at least two geometric quantities that have a physical interpretation. And the first one is the scalar curvature. So as you know, the scalar curvature is an infinitesimal quantity, so it also should have an infinitesimal meaning, and in particular, it provides a lower bound for the energy density of the Riemannian manifold MG. So in particular, if MG is physically viable, you would expect that the scalar curvature is non-negative. Okay, then on the other hand, the other quantity is the so-called ADM mass. So I'm also not going to define this, but this is a scalar that you can associate to the Riemannian manifold MG, which is a geometric invariant. So you can define this as a flux integral over a large coordinate sphere in the almost Euclidean part of MG. And it turns out that this quantity provides a measure for the total gravitational energy of MG. Okay, so now a very basic question that you can ask yourself is, if you have non-negative energy densities, if the scalar curvature is non-negative, then you would expect that this adds up to something non-negative globally also. And that this is the case was proven by Shane and Yao and later on by Witten independently, and this result is now known as the Riemannian positive mass theorem. And precisely what they showed is that if MG is asymptotically flat and has non-negative scalar curvature, then the ADM mass is also non-negative. And you also get rigidity in the sense that if the ADM mass vanishes, then MG has to be isometric to flat R3. So what this means is that on a purely qualitative level, the ADM mass is able to detect the presence of curvature under the assumption of non-negative scalar curvature. Okay, so now you could, of course, refine this heuristic. And right now, we just assumed that the space-time is flat and has non-negative energy density, but you could also assume that the space-time contains certain objects. And I think the simplest example is if MG contains a black hole. And in this case, you would hope that this ADM mass at least accounts for the size of this black hole. So to translate this into mathematical terms, we're going to assume that we have a closed minimal surface, which is two-sided. So now this closed minimal surface divides M into two components, all into bounded and one unbounded component. And let's call M prime the unbounded component of the complement of N in M. Okay, now we say that such a minimal surface is outermost if there are no other compact minimal surfaces in M prime. So in particular, N is not shielded from infinity by another minimal surface. Okay, so why do we care about minimal surfaces here? The reason is that such a minimal surface models the event horizon of a black hole in the space-time in the initial data set. And the condition of being outermost means that this black hole is actually visible to an observer who moves around in the universe. Okay, and the heuristic that I said before was due to Roger Penrose, and this was proven in the Riemannian case by Gerhard Huisken and Tom Illmann, and later independently by Hubert Bray. And what they showed is that if I have an asymptotically flat Riemannian manifold, and if n is an outermost minimal surface, and also you have non-negative scalar curvature outside of this minimal surface, then the ADM mass is greater or equal than the square root of the area of n divided by 16 pi. And equality holds precisely if m prime is isometric to 1/2 of the spatial Schwarzschild manifold. So here we call the spatial Schwarzschild models initial data for a single static black hole. So what this means in physical terms that if you have a black hole, then the ADM mass accounts at least for the size of this black hole. And if the ADM mass is equal to the size of this black hole, then there's no other matter apart from the single black hole. Okay, so let me say a few words about the proof of this result. So Huisken and Illmannen used, as many of you might know, inverse mean curvature flow to prove this result. So here the idea is that you start with the horizon and then you let it flow through the ambient space according to some parabolic partial differential equation. And here the idea is that a point x on the surface moves in direction of the outward normal nu and at speed of 1 over the mean curvature. So this is the reason why this flow is called inverse mean curvature flow, because you divide by the mean curvature and the speed of the flow. Okay, now the question is, of course, why is this a good idea? And the reason is that if the flowing surface n is connected, then the Hawking mass is non-decreasing along this flow, and the Hawking mass is given as the square root of the area of nt divided by 16 pi times 1 minus 1 over 16 pi times the integral of the mean curvature h of nt squared. So in particular, at time t equals 0, the mean curvature vanishes. So this is exactly the right-hand side of the Riemannian Penrose inequality. And now we can also show that as time t tends to infinity, this quantity is asymptotic to the ADM mass. So this is how you can bridge from the horizon to all the way out to infinity where the ADM mass is defined. Okay, then on the other hand, the proof of Bray is very different. So this is based on a conformal flow of the metric G. So here the idea is that you use an intrinsic flow of mg, so you evolve all of mg at the same time. So this is more in the spirit of Ricci flow, for example. And this conformal flow of Bray has some nice properties. So first of all, it turns out that the area of the horizon is constant along this flow, while the ADM mass is non-increasing along this flow. And moreover, Bray is able to show that as time t tends to infinity, this conformal flow approaches spatial Schwarzschild. And somehow this approach is better suited to prove the Riemannian Penrose inequality because it also works in the case where n has multiple components. So I forgot to say this, that the Hawking mass is really only non-decreasing if n is connected. So if it has multiple components, you really can show that it's not non-decreasing anymore. And on the other hand, the proof of Bray really also works in the case where n has multiple components, and you can even also extend it to higher dimensions. Okay, so this is what I wanted to say about the Riemannian Penrose inequality. And shortly after proving the Riemannian Penrose inequality, Huisken conjectured that a similar result should hold in the context of extrinsic geometry. Now, to state this conjecture, I need to introduce some terminology. And to this end, we're going to consider a connected, complete, unbounded surface S in R3, which has no boundary and has integrable scalar curvature. And now we leave the intrinsic world and now we consider extrinsic surfaces in R3. And now we say that such a surface S is asymptotically flat or an asymptotically flat support surface. If outside of a compact set, it looks very much like a Euclidean plane. So again, you have a compact set K where both topology and geometry of S might be very complicated, but once you leave this compact set, you hope that the geometry of S is more and more like that of a flat plane. So let's be a bit more precise over here. So we say that S is asymptotically flat if there is a compact set K and a function psi, which is smooth over R2, such that the complement of this compact set K is contained in the graph of psi, and such that you get control over the derivatives of psi. So we assume that the gradient of psi plus mod y times the Hessian of psi decays like big O for y to the minus 1. And here y is a point in R2, so a point in the plane over which S is an asymptotic graph. So again, this means that in a compact set K, S might be very complicated, but outside of this compact set K is a graph of a function psi, and this function psi has at most logarithmic growth. So you could be a little bit more lenient over here with the decay rate, but I'm just going to stick to the decay rate of -1 today to keep things simple. Okay, so as you know, the scalar curvature is a measure for the average curvature of a Riemannian manifold. On the other hand, the mean curvature is a measure for the average curvature of an extrinsic surface in R3. So in this analogy between asymptotically flat support surfaces and asymptotically flat Riemannian manifolds, you would somehow expect that the mean curvature plays the part of the scalar curvature. Now, on the other hand, it turns out that there's also a scalar quantity that stands in for the ADN mass, and this is the so-called exterior mass. And this exterior mass is defined as the limit as r tends to infinity of 1 over 2 pi. And now we take a large coordinate circle in the plane over which S is an asymptotic graph. And over this coordinate circle, we compute the radial derivative of psi. So in some sense, you could think of this exterior mass M as the slope at infinity of the surface S. So let me illustrate this over here. So here we have an asymptotically flat support surface S, which looks like a half-catenoid, and then you have somehow capped this off. And now in order to compute the exterior mass of the surface S, we take a coordinate circle, which is indicated over here by the dotted line. And then we compute the radial derivative over this coordinate circle over here and integrate it to obtain the exterior mass. Okay, now it will turn out that this half-catenoid is also a prime example of such an asymptotically flat support surface. There's also other examples, as we will see shortly. I mean, a very basic example is also a plane, but it turns out that there's many such surfaces, and we will see also later on why they are actually geometrically relevant. Okay, so now, as before, one very basic question that you can ask yourself is the following. So if the mean curvature is non-negative, this of course means that the surface S bends upwards on average. So that there might be directions in which the surface is bending downwards, but on average you would expect that the surface is bending upwards. So now if you have a surface which has non-negative mean curvature everywhere, then you would expect that the slope at infinity, so the exterior mass, should also be non-negative. And that this is the case was proven by Volkmann and later on in slightly greater generality by Almaraz, Barbosa, and de Lima. And what they showed is that if the mean curvature is non-negative, so is the exterior mass, and equality holds precisely when S is a flat plane. Okay, so this result looks, of course, very much reminiscent of the Riemannian positive mass theorem, and this led Huisken to conjecture that there should also be a result which somehow generalizes the Riemannian Penrose inequality. But in order to state this result, I need some more definitions. And first of all, as we can see from this picture over here, such an asymptotically flat support surface S, because in my definition, such a surface S has only one end. So in particular, it divides R3 into two components. So let's call M of S the component of R3 without S that lies above S. Okay, and now another thing that you can notice in the case of the half-catenoid is, so it's a bit difficult to see over here, but in the neck of the half-catenoid, there is a round disk that meets the half-catenoid orthogonally, and moreover, this surface, because it's a round disk, is a minimal surface. And for this reason, we make the following definition that we say that a surface D, which is contained in the region above S, is called a free boundary minimal surface if first of all it is a minimal surface, and second, it also meets S orthogonally along its boundary. Okay, so now the next thing that we need to define is, another thing that you can notice is that if you take the boundary of such a free boundary minimal surface, then the boundary divides the asymptotically flat support surface S into bounded components and one unbounded component. And we're going to call the unbounded component of the complement of the boundary of D in S S prime. Okay. All right. So now, of course, we want a proxy for outermost minimal surfaces in asymptotically flat Riemannian manifolds. So we say that D is an outermost free boundary minimal surface if there's no other free boundary minimal surface that is contained in the, so that is first of all contained in the region above S, which is M of S, and supported on the exterior surface S prime. So in other words, there's no other free boundary minimal surface that kind of lies above this outermost minimal surface D. Okay, so I have a diagram over here that illustrates this a little bit better. So again, we have a asymptotically flat support surface S over here, which is a half-catenoid that is somehow capped off with this hemisphere over here. And then the outermost minimal surface D over here is this round disk that meets the half-catenoid orthogonally. And as you can see over here, the boundary of this minimal surface D divides S into two components. One of them is bounded, so this is the solid black line over here. And the other one is unbounded, so this is the dotted line over here S prime. And now if you look for any other minimal surface that is supported on this exterior part of the surface S, so S prime, then you will find that it doesn't have a contact angle of pi over 2. And for this reason, we say that this minimal surface D is the outermost free boundary minimal surface of S, because there's no other free boundary minimal surface that is kind of outside of D in this sense. Okay, now one thing that you can check is if you look at the half-catenoid, or if you look at such a capped off half-catenoid, then the larger you make the size of the neck, so the larger you make the size of this outermost free boundary minimal surface, the larger the exterior mass becomes. Okay, and this led Huisken to make the following conjecture, which we subsequently proved about a year ago. So the statement is, if you have an asymptotically flat support surface S in R3, which has an outermost free boundary minimal surface D, and also you assume that the mean curvature is non-negative on the exterior part of the surface, then you can bound the exterior mass in terms of the size of D. More precisely, you get that M is always greater or equal than the square root of the area of D divided by pi. And you also get rigidity in the sense that equality holds if and only if S prime is a half-catenoid. Okay. All right, so before I move on how to prove this result, I want to convince you a little bit that these asymptotically flat support surfaces are actually a reasonable concept and not some ad hoc concept that people came up with so they could prove some results on. So to this end, let's consider a complete embedded minimal surface S tilde in R3, which has finite total curvature, and let's orient it by some choice of unit normal nu. So basic examples of such complete embedded minimal surfaces with finite total curvature is first of all a plane. And another example is, of course, a catenoid. And for a very long time, it was believed that these are the only examples. And then in 1980 or something like that, Costa found another minimal surface, which looks like this. So this is a minimal surface that has three ends. So two of them are catenoidal, one of them is planar. And as we can see, the planar end is connected to the catenoidal end by these two necks over here. And after these, after Costa's minimal surface was found, people actually discovered infinitely many such complete embedded minimal surfaces with finite total curvatures. So this is a very rich class of minimal surfaces that has been studied a lot. And one thing that you can see over here is that this minimal surface has three ends, like one of them is planar, the other two, the top end and the bottom end, are both catenoidal. And also what we can see is that these ends kind of start looking more and more like flat planes. Okay, and more generally, what you can show, if you have a general complete embedded minimal surface with finite total curvature, then such a minimal surface always has a finite number of ends. So in the case of the catenoid, it has two ends, Costa surface has three ends, other minimal surfaces have more ends. And each of these ends is contained in asymptotically flat support surface. So in particular, asymptotically flat support surfaces arise very natural as the ends of complete embedded minimal surfaces with finite total curvature. Okay, now it turns out that there are some natural quantities that you can associate to such minimal surfaces. And to define them, let's make some definitions. So the ends of such a minimal surface can be ordered in terms of their height. So let's say that S top is the top end of S tilde. And let M tilde be the component of the complement of R3 minus S tilde that somehow lies above this top end. So in case of Costa's minimal surface, this component M tilde would be all the way up here. Okay, and now with that in mind, we're going to define the flux of the top end by integrating the outward conormal of the top end over the boundary of the top end. Okay, now you might think that this is not a well-defined definition because it somehow depends on the size of the top end, but it turns out that it actually doesn't. And the reason is that if you change the top end by adding or subtracting some compact set, then this vector over here doesn't change. And the reason is the first variational formula because it still has mean curvature 0. Okay, so this is one classical quantity that you can associate to such a minimal surface. And the other quantity you can associate to such a minimal surface is the so-called neck size. So for such a minimal surface, as I told you, it divides R3 into two unbounded components. And now you can ask yourself, if I want to divide the unbounded component which sits above S tilde into, again, two unbounded components, how much area do I need for this? So in other words, neck size is the smallest amount of area needed to divide M tilde into two unbounded components. So let's again illustrate this over here. So if I wanted to divide the region M tilde into two unbounded components, what I would like to do is that I fill in these two necks over here of Costa's minimal surface. So in particular for Costa's minimal surface, the neck size is realized by two minimal surfaces. Okay, and now it turns out that our result gives the following nice corollary, which yields a new characterization of the catenoid in terms of purely extrinsic quantities, which is quite nice because there's many other characterizations of the catenoid among complete embedded minimal surfaces with finite total curvature, but all of them somehow involve the intrinsic geometry of the catenoid, and this result only purely involves the extrinsic geometry of the catenoid. So the corollary that we get is if we have a complete embedded minimal surface with finite total curvature, then the flux of the top end is always greater or equal than the square root of 4 pi times the neck size of S tilde. And if equality holds, then S tilde has to be either plane or catenoid. So in other words, if you ever find yourself on a minimal surface and you're able to compute the flux at infinity, then you know how much area you need to divide the region above this minimal surface into two unbounded components. And if you need exactly the amount of area that you computed, then you know that you must be on a catenoid. Okay, so let me quickly present the proof of this corollary. So you can show that neck size is realized by some surface d tilde. So this is the surface of least area that divides M tilde into two unbounded components. And by the first variational formula, you can check that d tilde is a free boundary minimal surface. Okay, so now the boundary of d tilde bounds the top end of M tilde. And now we can extend this top end to an asymptotically flat support surface S. And this asymptotically flat support surface S now supports a free boundary minimal surface d tilde. Okay, now of course the top end, or this asymptotically flat support surface S has some exterior mass m, and you can also show that it supports an outermost free boundary minimal surface d. But we also know that d tilde is area minimizing in its relative homology class. For this reason, we know that the area of d tilde has to be less or equal than the area of d. Okay, finally, what you can show is that the flux of the top end equals 2 pi times the mass of the asymptotically flat support surface S that contains the top end. And now, for this reason, we know that the flux of the top end, or the length of the flux of the top end, is equal to 2 pi times m. And by the extrinsic Penrose inequality, we know that this is greater or equal than the square root of the area of 4 pi times the area of d. And by what I said previously, this is greater or equal than the square root of 4 pi times the area of d tilde. So this is how you can prove this corollary using Penrose inequality in extrinsic geometry. Okay, so in the remaining time, I want to talk a little bit about the proof of the main result. So let's again recall this result. So we have an asymptotically flat support surface S. We assume that it supports a free boundary minimal surface D. And we also assume that this free boundary minimal surface D is outermost. Okay, and moreover, we're going to assume that the mean curvature is non-negative on the exterior part of the surface S. Okay, and then the claim is that m is always greater or equal than the square root of the area of d divided by pi, and the equality holds precisely when S prime is a half-catenoid. Okay, and here are again these definitions. So half-catenoid looks like one half of the catenoid. In this case, the half-catenoid is contained in some asymptotically flat support surface that is obtained by capping the half-catenoid off, which is indicated by the solid black line. And then the free boundary minimal surface D here sits in the neck of the half-catenoid. S prime, the exterior surface, is this dotted line over here. And we denote by M prime of S the so-called exterior region of the asymptotically flat support surface. So this is the part of the region above S that sits outside of the free boundary minimal surface D. Okay, so before I prove the result, I want to show you some other ideas that you could use to prove this result that don't work. And the reason why I show you this is that I somehow want to convince you that you have to come up with a new idea to prove this result, and that you can't just simply employ the methods that were used in Riemannian geometry to prove the Riemannian Penrose inequality. Namely, in some previous work based on inverse mean curvature flow, I could prove the Penrose inequality in extrinsic geometry in the case where D is connected but with non-optimal constant. So what I obtained is that M is always greater or equal than the square root of the area of D divided by 2 pi. And using a different approach together with Michael Eichmair, we were able to show that this inequality holds also in the case where D is not necessarily connected. So note that we have a factor of 2 over here, so in particular, this result is not optimal. Okay, so what are the ideas behind these approaches over here? So for the first approach, you can observe that if you again look at the region above the half-catenoid, then this region is foliated by spherical caps that meet the half-catenoid orthogonally. So these surfaces, these spherical caps, are indicated over here by sigma tilde r, where r corresponds to the radius that produces this spherical cap. And now you might say, so what? But it turns out that this foliation actually has a nice property, because you can show that this following quantity over here is independent of the radius that produces these spherical caps. So in particular, it's constant along this foliation, and the quantity is given by the length of the boundary of the spherical cap divided by 2 pi times 1 minus 1 over 8 pi times the integral of the mean curvature squared. Okay, so now, of course, this quantity looks very similar to the Hawking mass. And for this reason, I had the idea they could maybe use inverse mean curvature flow to prove the Penrose inequality in extrinsic geometry. And indeed, I was actually able to show the existence of such a flow in the setting of asymptotically flat support surfaces, where the speed of the flow is given by 1 over the mean curvature, and the flowing surface is required to stay perpendicular to the support surface. But unfortunately, even in the case of the half-catenoid, this flow doesn't go through this foliation over here. So in particular, this quantity is not constant along this free boundary inverse mean curvature flow. And for this reason, you cannot use this flow to produce an optimal result. So this is why we get this constant of 2 pi in the inequality, which is not optimal. Okay, so on the other hand, we could maybe think that you could reduce this result to the Riemannian Penrose inequality, so that the extrinsic Penrose inequality is just a Riemannian Penrose inequality in disguise. And to this end, what you can do is that you take 2 copies of the region above S. And now, because the region above an asymptotically flat support surface asymptotically looks like a half space, if you glue 2 of them together, you would expect that you get an asymptotically flat Riemannian manifold. So this is somehow illustrated in this diagram over here. We take 2 copies of an asymptotically flat support surface, and we glue them together along the exterior surface S prime, which is over here indicated by the solid black line. So we somehow leave the extrinsic world and produce an intrinsic Riemannian manifold. Now again, because asymptotically M prime of S looks like a half space, if we glue 2 copies together, this should look like asymptotically like flat Euclidean space. Now, because D meets S at a contact angle of pi over 2, we expect that the contact angles match up. So the 2 copies of D should produce a minimal surface, which we expect to be outermost. And now, of course, this glued space is not going to be smooth, but because the mean curvature of S prime is non-negative, we can smoothen along the edge using the methods developed by Pengzi Miao. And this should then produce non-negative scalar curvature. So it turns out that you can make all of this rigorous, and you can even relate the exterior mass of S to the ADM mass of the glued manifold and apply the Riemannian Penrose inequality to the glued manifold. But somehow when you do this, you give up too much information and you end up with the same inequality over here. So you again get this factor of 2 pi, which is not optimal. Okay, so what this goes to show you is that you somehow have to develop a new idea to prove this result. And to illustrate this new idea, let's again look at the half-catenoid. So it turns out that there is another foliation of the half-catenoid that is very natural, and this foliation is by taking the intersection of the half-catenoid with horizontal planes. So this produces these surfaces sigma t over here, which are simply the intersection of the region above the half-catenoid by planes of height t. Okay, so one thing that you can also notice is that, for example, taking the surface sigma 1 over here, the boundary of this surface sigma 1 together with the boundary of D bounds a compact subset on the half-catenoid, which is illustrated by the dotted line over here. And we call this bounded subset, which is a subset of the support surface. We call this the lateral area of the surface sigma t. And we call the area of this bounded subset S of sigma t the area enclosed by sigma t. Okay, now there's a few basic observations that you can make about the surfaces sigma t. So first of all, you can show that sigma t is a minimal surface, but maybe what's more interesting is that sigma t is actually a minimal capillary surface. So what this means is if you compute the contact angle of sigma t to S, which is given by the inner product of the normal of S and the normal of sigma t, then this doesn't depend on where you are on the boundary. So this is equal to a constant. And let's say that we've chosen an angle theta t so that this is equal to the cos of theta t. Okay, so far this might not be so interesting, but what's remarkable is that there's again a very natural quantity that is constant along this foliation. And this quantity is given by the sine of the contact angle times the square root of sigma t. Okay, so this is of course very promising because such constant quantities can always be used to prove geometric inequalities. But now if we wanted to reproduce something like this in a general setting, we would hope that these surfaces sigma t arise in a variational way. And it turns out that they actually do. So if you take one of these surfaces sigma t, and you take any other surface supported on a half-catenoid whose enclosed area is the same as that of sigma t, then you can show that the area of the other surface has to be strictly larger than that of sigma t. So in other words, sigma t has minimal area for the area it encloses. So in particular, it solves some isoperimetric type problem. Okay, so now with these observations in mind, it's kind of clear what we can try. So let's consider an asymptotically flat support surface S. Let's assume that it supports an outermost free boundary minimal surface D. And let's assume that mean curvature is non-negative on the exterior part of the surface S. Okay, now for every positive number Z, we consider the following variational problem, that we minimize area among all surfaces supported on S that are contained in the exterior region of S, whose enclosed area is equal to Z. So each amount of enclosed area, we minimize area. And there's nothing wrong with considering this infimum, and we can also give it a name. So let's call it rho of C, and we're going to call rho the profile function of this isoperimetric type problem. Okay, so of course we can consider this variational problem, but it might not be well behaved, and there is also no reason that for all values of C this should be solvable. But just for the sake of exposition, let's now assume that first of all rho is smooth. So in general, there's really no reason to believe this. But let's assume this for now, and also maybe more importantly, let's assume that we can actually solve this variational problem. So in other words, we're going to assume that for every positive number Z, we can find a surface sigma Z which is supported on S, such that first of all the area enclosed by sigma Z is equal to Z, and moreover that rho of Z is equal to the area of sigma Z. So in other words, the surface sigma Z encloses area equal to Z and has minimal area for the area it encloses. Okay, so once we have this, we can run the usual business in the calculus of variations. So first of all, we can study the first variational formula. And so first of all, you can see that sigma Z is a minimal surface. I think that's maybe quite obvious because if you have a boundary curve on S that bounds a certain amount of enclosed area, then you would of course choose the solution of the plateau problem to fill in this boundary curve. But maybe what's more remarkable is that sigma Z is actually a minimal capillary surface. So you can explicitly compute the capillary angle, and it turns out that it's equal to, or that its cos is equal to minus rho prime of C. Okay, so now to study the second variation, we need to choose some sort of variation of sigma Z. And the most basic thing that you could do is that you choose a normal speed, a unit normal speed variation. So it's exactly what we're going to do. So we consider a family sigma delta, which is going to be a perturbation of sigma Z. So this means that sigma of 0 is equal to sigma Z. And that the speed of this foliation at delta equals 0 in normal direction is equal to 1. Okay, so one thing that you can observe is that rho of the area enclosed by sigma delta has to be less or equal than the area of sigma delta. So this is simply by the definition of rho, because rho is the infimum of area needed to enclose a certain amount of rho is the infimum of area that you need to enclose a certain amount of enclosed area. But on the other hand, we also know that equality holds when delta is equal to 0, because sigma of 0 is equal to sigma Z, and sigma Z solves this variation problem. Okay, so for this reason, we can perform the second derivative test to this inequality over here. And this gives us an upper bound for rho prime prime of Z. So first of all, we get some terms coming from the first variation of enclosed area. And this gives us 1 minus rho prime of c divided by the length of the boundary of sigma z squared. And on the other hand, we also get some terms coming from the second variation of area formula. So the first one is minus the integral over the length of the second fundamental form squared, which I denote by h. And then we get minus, there should be 1 over the square root of 1 minus rho prime of c squared times the integral of the mean curvature squared. And finally, we also get the integral over the boundary of sigma z of the geodesic curvature of sigma z. Okay, so we have to use the assumption that that S has non-negative mean curvature somewhere. And we actually do use it in multiple places. They've kind of swept under the rug, but we also use it to get rid of this term here. So using that the mean curvature is non-negative, we can throw away this term. And we're also going to throw away half of this term over here. Okay, so now this term here is of course non-negative, but as you might expect, we can do better, because if knowing that sigma z is a minimal surface, we know that 1/2 times the length of the second fundamental form squared is equal to minus the Gauss curvature. So we can combine these two terms over here, so the length of the second fundamental form and geodesic curvature, using the Gauss-Bonnet theorem. So they are equal to 2 pi times the Euler characteristic of sigma z. And now if sigma z is connected, we know that the Euler characteristic can be at most 1 because sigma z has boundary. So in particular, these two terms are less or equal than 2 pi. Okay, so now somehow we've estimated all quantities apart from the perimeter of sigma z, and a priori this doesn't have to be related to rho in any way. But fortunately, we can estimate this term using the optimal isoperimetric inequality for minimal surfaces. So this is a pretty deep result on minimal surfaces that was proven by Kalimann in the case of minimal disks, and subsequently in increasing generality by Almgren and Brentley. And what this result tells you in 2 dimensions is that if you have a minimal surface, then its perimeter squared is always greater or equal than 4 pi times its area. And equality holds precisely when the minimal surface is a round disk. Okay, so in our case, this is good because we know that the area of sigma z is just equal to rho of c. Okay, now if we combine all of this, we see that 2 times rho prime prime of c times rho of c is less or equal than 1 minus rho prime of c squared. And now we can, of course, integrate this differential inequality. And what we see from this is that 1 minus rho prime of c squared times rho is non-decreasing. And this is, of course, very good because this is precisely the quantity that we discovered on the half-catenoid. Because rho is the area of sigma z, and 1 minus rho prime of c squared is the sine squared of the contact angle. Okay, so there's maybe one thing that is potentially very dangerous about this strategy, and namely that I assumed over here that sigma z has to be connected. And there's really no reason that this should be the case. So even in the case where the outermost minimal surface D has only one component, there's no reason to believe why for large values of z, sigma z might not have multiple components. But fortunately, you can work around this problem by choosing a different variation. And namely, what we do instead is, if sigma z has multiple components, that you adjust the normal speed on each individual component. So rather than choosing it to be constant, you choose it to be locally constant. And the speed on the individual component, on the kth component, is given by the perimeter of the kth component divided by the square root of the length of squared of the perimeter of the other components. So somehow you choose some sort of weighted average for the normal speed of this variation, which is different on each component. So let me illustrate this over here. In this example, sigma z has 2 components, and one of them, sigma 1, has smaller perimeter than sigma 2. For this reason, we flow sigma 2 further out than sigma 1. Okay, now I'm not going to go into details, but it turns out that if you do all of this, you can still obtain the same differential inequality over here. So even in the case where you have multiple components, the entire argument works. You might have to work a little harder, but everything can be done exactly the same way as before. Okay, so because I don't have so much time left, I think I'll skip this slide. But what you can show is that if you compute this quantity over here, so square root of 1 minus rho prime of c times square root of rho, that up to a constant, this is asymptotic to the exterior mass. So to this end, you somehow need to study how these minimal capillary surfaces sigma c look like as you increase c, and it turns out that you can explicitly compute this limit. And now putting everything together, what we see is that the square root of the area of d divided by pi, that this is of course equal to the square root of 1 minus rho prime of 0 squared times rho of 0 divided by pi, because when we minimize area given 0 enclosed area, we just simply obtain the outermost free boundary minimal surface, and because the contact angle is pi over 2 rho prime of 0 is equal to 0. Okay, now we know that this quantity here is non-decreasing, so this is less or equal than the limit as c tends to infinity of this quantity. And in the slide that I just skipped, you can show that the limit over here is actually equal to the exterior mass. Okay, so this is how you obtain the inequality. And now finally, just very briefly, we'll have to consider the case of equality. Now, if equality holds, there's two things that you can observe. So first of all, in this estimate here, we throw away the mean curvature. So we know that the mean curvature of S has to be 0 along the boundary of sigma z. And also we have the isoperimetric inequality, and we have to have equality there too. So we know that every surface sigma z has to be a minimal disk, and actually a flat disk. Okay, now if you combine all of this, you can, putting in some additional work, first of all show that S prime has to be a minimal surface. And you can even show that the topology of this minimal surface has to be an annulus. And also you can compute the integral of the Gauss curvature of this minimal surface, and this turns out to be equal to minus 2 pi. Okay, also from this argument, what you know is that the free boundary minimal surface D has to be a round disk. So in particular, you can reflect the minimal surface S prime across this round disk, and this now gives you a minimal surface without boundary that still has the topology of an annulus, and you know that its total curvature has to be twice the total curvature of S prime. So now you have a minimal annulus, which is complete. It might not be embedded because when you reflect it might self-intersect, but it's for sure immersed. And you know that the integral of the Gauss curvature is equal to minus 4 pi. And now a very classical result of Robert Osserman shows you that such a minimal surface has to be a catenoid. So in particular, the non-reflected surface has to be a half-catenoid. Okay, so I'm at the end of my talk. Thank you very much for your attention.
Okay, are there any questions for Thomas?
I have
Oh,
sorry. I have a couple of questions, if possible.
Mhm.
Okay, Thomas, one is it possible to apply your argument? You consider a surface in R3, but I don't know, in some manifold or with the rich non-negative, with the asymptotic volume ratio positive or asymptotically flat. Okay, maybe you don't have the rigidity, but some inequality.
Yeah, it's a good question. I think the problem is, so when you apply the isoperimetric inequality for minimal surfaces, this is a very much Euclidean result. And I don't think that there is an analog for sure there is no analog in non-negative scalar curvature.
But for Avoer positive, yes.
For Ricci positive, you mean?
Yes, there is some theta, if I remember here.
Yeah, I think there's a paper of someone
Brandon.
Bentley, right? Yeah, which
Yes.
analyzes this result. Yeah, it's a good question. I mean, so I kind of never thought about non-negative Ricci. I just thought that for non-negative scalar curvature, there's nothing you can do. But it's true for non-negative Ricci, maybe for certain cones, you could classify them or something like that. Um, I guess you would probably want to look at a slightly different problem then, right? Um, hmm.
Mm.
But yeah, it's a good point. I mean, for non-negative Ricci,
Yes, no, no.
yeah, I think that's certainly something that you should look at because I think when you can I mean this argument kind of works whenever you can apply the isoperimetric inequality. This is kind of the only Euclidean thing you use, and as you say, this is also possible in non-negative Ricci. So there might be some applications there, yeah.
Okay, and second. Another question, but it is very strange. Always in these slides, you can consider now sigma with the multiple connected components, since you adjust the flow in, and is it possible, I don't know, for also inverse mean curvature flow, similar maybe, or it is completely different?
So for inverse mean curvature flow, this doesn't work. Like, so if you, for example, if you take an asymptotically flat Riemannian manifold, which
Okay.
has two Schwarzschild black holes, which are very far away from each other, and then you compute the Hawking mass along inverse mean curvature flow, then you see that it actually goes down. So it's really not a problem with the Gauss-Bonnet theorem. The problem is really that that the Hawking mass is not non-decreasing along inverse mean curvature flow when you have multiple components. So you can really produce counterexamples. And I think so somehow the reason why this works and why it doesn't work for inverse mean curvature flow is somehow inverse mean curvature flow is approximately modeled on isoperimetric surfaces, right?
Mm-hmm.
And the problem with isoperimetric surfaces on a very heuristic level for these arguments is that somehow area scales differently than volume. But in this example here, the two quantities that we consider is area and enclosed area, and both of them are two-dimensional. And this is very heuristically why in this case somehow you can work around this issue of having a connected surface. Whereas for Riemannian Penrose, you can't. So I think what might be the right approach if you wanted to prove Riemannian Penrose this way, then I think you somehow have to consider a different variational problem where you use some sort of weighted area weighted volume, so that volume somehow becomes two-dimensional too, if this makes any sense. So that asymptotically volume also scales like squared and not cubed. So you somehow have to, I think, that this is the right approach, that you scale volume in a way that it grows less at infinity, if this makes any sense. But yeah, just using inverse mean curvature flow, you really cannot work around the issue that you only have one component.
Okay, thank you so much.
Yeah, thank you.
Well, I have a question about like if you start your surface not exactly at the free boundary position and you start it with some constant angle, would that give you something?
Yeah. So then the assumption that you have to make is that that the capillary minimal surface has to be a minimizer of the free energy. So the free energy is something like you minimize area minus contact angle times enclosed area. And then you can also show that the exterior mass has to be greater or equal than sine of the contact angle times the square root of the area of the capillary surface. So this also works for other capillary surfaces. And actually, so this positive mass theorem that I wrote down over here. Um, So this one, you can actually prove this way. So in general, you kind of expect that you have a free boundary minimal surface, but you can show that if S is not flat, then it supports a capillary surface. And then you can bound the exterior mass in terms of the area of these capillary surfaces, which then gives you that the exterior mass is positive, but this estimate might be very bad because when the contact angle is very close to being tangential, then of course sine of the contact angle is very, very close to zero.
Oh, thank you.
Yeah, welcome. Thank you.
Okay, let's thank Thomas again. And it was a great talk. Thank you. So.
Thank you very much.